dynamic equilibrium. And today I want to get that into notes and in a way that you'll be able to kind of recite and regurgitate for exams and so on. So today's date, so your filing's nice and neat, you've got a nice organised folder and everything is there. So we learnt yesterday when we were talking that some reactions are reversible. We learnt that sometimes A can turn into B and B can turn back into A. And we have an arrow like that to show that we've got a reversible reaction going on, right? So we've got a reversible reaction, A is turning into B and B can turn into B can turn back into A again. We also learnt when we were talking about that, since we've been doing a bit of revision and again this morning of the energetics topic, that if the forward reaction is exothermic, the reverse reaction must be endothermic. But even more specifically than that, if the forward reaction is exothermic, say it's minus 100 kilojoules per mole, the reverse reaction must be endothermic and it'll be plus 100 kilojoules per mole. So the energy changes for the processes are equal and opposite. And that's something that's really worth being aware of, and you're expected to know that. We said that an example of this process, kind of a physical example of this process, I can't remember if we talked about this example or not, it might be an iceberg, say. An iceberg might be sitting in the ocean, and ice on the surface of the iceberg might be melting to make water. There might be some water freezing back on the surface again as well, though. So it's a process that's going back and forth all the time. But in chemistry, there's lots of examples of these, and we don't mention them really much at all, even though they're happening all the time until about now in the course. Now, we're particularly interested in the situation of reactions when they reach what we call dynamic equilibrium. And this is when dynamic equilibrium, this is a definition you have to learn. Equilibrium. Dynamic equilibrium is when the rate, of the forward and reverse reactions are equal. And this can only happen in a closed system. So it's when the rate of the forward reaction and the reverse reaction are the same. Now, we talked about the fact that this could be a situation where there's 50% A and 50% B, but it could also equally be a situation where it's 90% A and only 10% B. As long as A is turning into B at the same rate as B is turning into A, it's what we call a dynamic equilibrium. In other words, the concentrations at equilibrium of each of the reactions, of reactants and products is not changing. So the concentration of them stays the same. So let's add that as a nice detail then. So the concentrations of reactants and products doesn't change. But it is also worth saying they don't need to be equal to each other. Okay, let's pause it there for a second. I probably should define closed system just to be really clear for you. A closed system is when reactants or products are not allowed to escape. Now, what I'd like to do is to kind of represent this with a graph if I can. Now, these graphs look kind of scary and confusing, I think, to start with for people, but it'll be okay, we'll get there. So, I'm going to draw two different types of graph. Just sketch these graphs with me. If I put ROR, that's just rate of reaction. And over here we've got time. So what I'm going to do is going to draw the graph to start with. And I'm going to talk you through what's going on. And you'll see this graph I've drawn here is on the sheets that I've given you that we're going to use a bit later on today. I'll give you a moment to sketch that and then I'll talk you through what's happening. This is a really nice opportunity, isn't it? And I could hear you talking about this just now, to revise what's going on in the rates of reaction topic. In fact, the way that the GCSE for AQA sets this topic out, it is as part of the rates topic. We separate it out because I think it's helpful to do so. I think this is a bit harder than rates, so I like doing it in year 11. But you might remember that if you've got A, we're just going to stick with A going to B for now. In the forward reaction, A is turning into B, and the reverse reaction, B is turning into A. So in that forward reaction, at the start, with any reaction, you would start with just the reactant, wouldn't you? And then you'd allow it to proceed. At the start, you've got a high concentration of A, because that's all you've got in the pot. And so if you've got a high concentration, you've got a high rate. So the graph is steep, and the concentration of A is decreasing over time, so the rate slows down over time. So this is not concentration, this is rate. But as A is used up, the concentration decreases, so the rate decreases. So the graph is steep at the start. We've got a steep tangent, if you like, there. As the reaction proceeds, the graph shallows, and eventually you steady off here. So the rate eventually of A turning into B gets to that horizontal level. And at the start here for the reverse reaction, there is no B. And so the reverse reaction of B turning into A is very, very slow, which is why it's 0 here. Yeah, I got a bit muddled there when I was talking, but the point I was making, as A turns into B, the rate decreases. The rate at which the rate decreases slows down, which is why the gradient decreases. But all you need to spot here is the rate of reaction is decreasing as the reaction proceeds, because the concentration of A is going down. This arrow here, the reverse reaction, B turning into A, the rate is very, very slow at the start. It's 0 at the start because it is no B. But as soon as B starts to form, because A has turned into B, the rate of reaction will gradually increase. And eventually, as most of you spotted, they get to the same rate in the end. And when they meet that point there, that's the point at which dynamic equilibrium has been reached. Dynamic equilibrium has been reached, the point where the rates of reaction of the forward and reverse reactions are the same. Okay. There is another way of sketching this graph as well. So I'm going to draw this and then talk you through another way of thinking about this reaction too. Yeah, so another way of representing this will be with a concentration time graph. And before the reaction has reached equilibrium, we start in the pot with just A. So the concentration of A is very high. But as the reaction proceeds, A is used up, so the concentration will decrease. And you end up with eventually the concentration of A not changing at all. But as the reaction proceeds, we start with no B, and the concentration of B goes up sharply to start with, which is when the rate is at its fastest, when the rate of the forward reaction is at its fastest. And then gradually we end up with it shallowing, and eventually they end up unchanging. So the concentrations don't have to be the same as each other, but at the point where they're no longer changing, about there somewhere, is when we've got dynamic equilibrium being reached. So quite complicated. you're unlikely to have to produce or even discuss those graphs at GCSE. That graph could have looked like this. They don't have to look like that. They could look like this. The concentrations don't have to, they can cross each other like so. It's the point at which the concentrations are no longer changing is the important thing. So when they're about there somewhere, the graphs flatten off. Okay. Right. So the important thing you know though is what you're going to have to do is do it verbally and say the rate of reaction of the forward and reverse reactions are the same as each other, and that can only happen in a closed system. And the concentrations of A and B do not change. That's the key message. So what we've put at the top there in words is what you really need to know. Okay. So I really like this stuff, and we made a really good start on this talking about it yesterday, but not writing anything down. So we're going to think about some real examples today of this, and we're going to learn what we need to say in an exam and so on. And we're going to start off, I think, just talking about generic examples of A and B and C and D, and we'll worry about applying it to real examples later on. But we'll kind of think about the factors that can affect the position of equilibrium. So equilibrium doesn't have to be 50-50. It could be 90-10 or 10-90 or 50-50 or anything in between, 99-1, as long as the rate of reaction is the same in the forward and reverse direction. So let's start by thinking about the factors that can affect it, and we're going to start by talking about pressure. And so we must think about, only consider gaseous molecules. And what we talked about yesterday is this idea of Le Chatelier's principle. And Le Chatelier's principle, sort of simply put, is the idea that whatever I try to do to the reaction, or whatever you try to do to a reaction, the position of equilibrium will shift to oppose that change. So let's write down what that is here. So whatever change, sometimes they say words like imparted on the reaction, whatever change you try to make or you make to a reaction, the position of equilibrium will shift right or left towards the products or towards the reactants to oppose that change. And so if you remember that all the time, just think about chemical reactions as awkward year 9s. You tell them to be quiet, they get louder, or whatever it is. So whatever you try to do, they will try to oppose that change. And we kind of started to get our heads around it, but let's give an example here. So if we've got reactant A, which is a gas, reacting with 2 moles of reactant B, which is a gas, and that gives 2 moles of C, which is a gas to start with. Notice that all gas is here, and so we consider all of the substances. Now sometimes in exams they put a solid in there to confuse you. Now, which side, the left-hand side or the right-hand side, left-hand side with 3 molecules of gas and the right-hand side with 2 molecules of gas, which side would cause the highest pressure, assuming you've got the same number of moles of A, if you see what I mean? All things being equal, which side would be the highest pressure? Left or right, everybody? 3, 2, 1. Okay. Yeah, right. So if I try to increase the pressure, it will try to decrease the pressure. To decrease the pressure, the equilibrium will shift to the side where there's only 2 moles of gas. And essentially that's all we've got to say in an exam. We do not have to understand that well enough to explain it happily. Even at Key Stage 5, the explanations are really light here. Okay, so So what we'd say is there are three molecules. This is almost an exam answer now. There are three molecules. If you want to, you can say moles of gas. I'm going to underline of gas because I want you, when you're revising, to remember to say of gas when there's gases involved and we're talking about pressure, because without it, it's meaningless. There are three molecules of gas on the left and only two on the right. So if I increase the pressure, so in other words, I take the reaction vessel and somehow I squeeze it, or I add more gas to it to try to increase the pressure. So if I increase the pressure in some means or another, take it from 1 atmosphere to 2 atmospheres or whatever it might be, the position of equilibrium will shift to the right hand side to oppose the change made. It's quite a long answer, but it could be worth a heap of marks, right? And that means we'll produce more C. So if we're a manufacturer and our job is to make C and we make a lot of money for making C, we're going to want to make the pressure as high as possible to make as much of C as possible, right? So this stuff is really important in real world, and we'll look at an example of that, an example called the Haber process where they're making ammonia. And in that example, they do try to increase the pressure to shift the equilibrium to the right to make as much ammonia as possible, to make as much money as possible. So what this does is this causes something called, this increases the amount of C you get. So we say this increases the equilibrium yield of C. Now you can learn that perfect answer. You can learn how to do that. You're very, very capable of doing that. But that's what you've got to be able to say there. If I reduce the pressure, everything would be the opposite. You'd say there's 3 molecules of gas on the left and only 2 on the right. And if I decrease the pressure, the equilibrium will shift to the left to oppose the change made. This decreases the equilibrium yield. We don't need to write that out. It's just the opposite now. And we're going to do lots of practice of this, so don't panic if this is kind of scary. We do need to spot, though, as examples when there might be solids thrown in there. So let's think of an example. In fact, again, I'm going to stick with the A's and B's and C's for now. So in this one, we're just going to talk about it a moment. We're not going to write the whole thing out again. I'm going to say to you, and you're going to point for me, either to the right-hand side of the room or the left-hand side of the room. So what I'd like you to do, just drop your pens for a second. I don't want you to write anything for a moment. Just want you to listen and think. Put pens down. So with this example, I'll give you thinking time. If I crank up the pressure, no, if I reduce, what am I going to do here? I'm going to reduce the pressure of this reaction. I want you to tell me which direction the equilibrium would shift. So point either to the left of the room or to the right of the room now. I'm going to decrease the pressure. What's it going to do? Have a bit of thinking time and then show me which way it's going to go. And I'm going to decrease the pressure. So it's going to want to increase the pressure to oppose the change. So which way is it going to go? Point when you're ready, please. So with a bit of a nudge, you got there. Now every time I teach this for the first time, people struggle, but we're getting there with it now. So on the left, there's 2 moles of gas. So left-hand side, 2 moles of gas. Right-hand side, 1 mole of gas, because we're ignoring the solid and liquid because they don't take up any space. If I decrease pressure, equilibrium will shift to the left hand side to oppose the change. The reason for that is, or a way of thinking of it at least, the reason for it is I decrease the pressure, it wants to increase the pressure, and so it shifts to the left to try to oppose the change I've made, because there's 2 moles of gas there and they'd have a higher pressure than the 1 mole of gas on the right hand side. So the equilibrium shifts left to oppose the change. And so the last thing you have to say is, so equilibrium yield of the products, which are C and D, decrease or decreases. So that's the approach we've got to take again and again and again now. We're going to do a few examples verbally, and then we're going to write up some more examples of this in a sec. So we're getting there now. We discussed an example of a reaction here. So we took this reaction, which we'll learn about in some detail, the Haber process. This is a reaction between nitrogen and hydrogen to make ammonia. We'll learn about this in a different lesson. But on the left hand side we've got 4 moles of gas. And on the right hand side we've got 2 moles of gas. And so to increase the equilibrium yield, we said we increase the pressure. So if we increase the pressure, the equilibrium position shifts to right hand side to oppose the change I've made to it, and that causes the equilibrium yield to go up. Again, just practicing this over and over in class is what you need, but it's worth having a few notes on this so you can practice it at home as well. We also just talked on the board for a while about the effect of temperature, so we're going to start writing that up as well now. Oops, that's not the right letter E, is it? Effect of temperature. Let's leave it like that. The effect of temperature now. So it's just Le Chatelier's principle again. So whatever I try to do to a chemical reaction, whatever change I impart on a chemical reaction, the position of equilibrium changes to oppose the change that I've made to it. It's the same idea again here. So we'll stick with a simple idea of A turning into B, and this reaction is exothermic. In the forward direction. So you can either show that by writing exo over the forward arrow and endo over the reverse arrow, or you can show it by saying the enthalpy change for the forward reaction is usually written over there somewhere. So that tells you it's exothermic as well. So just like with pressure, equilibrium shifts to oppose the change. Now it's worth remembering, isn't it, that exothermic reactions cause the temperature to go up, and endothermic reactions will cause the temperature to go down. So if I increase the temperature, it will shift the equilibrium position to try to decrease the pressure, temperature, and this vice versa. So let's give an example of that then. and how we'd write it in an exam. So if I So we've got two things going on, what I do to it and what it tries to do to oppose my changes. So if I increase the temperature of the reaction, and I might do this, why might I do that, by the way? Why might I want to heat up a chemical reaction, please? Yeah, so nice answers. So if the reason you might want to increase the temperature to increase the rate, and it's worth practicing at this point, that increases the kinetic energy of the particles, which increases the frequency of collisions of the particles, also increases the probability of the collisions being successful. And some of you missed out that last bit there. But anyway, if I increase the temperature of the reaction, the equilibrium position will shift to the left hand side to oppose the change. Look at the language I'm using again and again, to oppose the change I've made to it, to oppose the change made. And that works because and you just have to state this in the exam, because the reverse reaction is endothermic. You can equally say the forward reaction is exothermic, it doesn't matter. But given the equilibrium shifting to the left, it makes more sense to me to say that that reaction is endothermic. All right? So that will cool it down. And that's it. I could do 20 examples, but they'll all be exactly the same here. If it's endothermic one way, it'll be exo the other way. What I'm going to do is I'm going to stop there, and we're going to do a little bit of practice of this for the last. Can we do one more thing? We might be able to squeeze one more thing in. We'll squeeze one more thing in. So we'll practice this lots next time once we've got the exam out of the way, the test out of the way of energetics. So the effect of adding or removing. The effect of adding or removing substances. So if I've got, let's do the same reaction yet again. We'll really step it up this time. We'll do A and B goes to C and D. Le Chatelier's principle is whatever you do to a reaction, it will try to oppose the change by shifting equilibrium. So if I add a load of A to this chemical reaction, it's going to want to try to reduce A. So which way is the equilibrium position going to shift? Point left or point right now? So very briefly then, and we'll come back to this and some other ideas. So if I add A, more A than there was, to a reaction that was happily at equilibrium, I chuck a load of A in, and as you pointed out, that wouldn't be at equilibrium anymore. It wouldn't have been a closed system for that time. If I add A, the equilibrium position shifts to the right hand side to oppose the change. And really importantly, for increasing equilibrium yield, what I might sometimes do if I'm trying to make C, and I make money from making C, if I remove C from the pot, and you'll see that there's a real example that we have to know about. If I remove C, likewise, the equilibrium position shifts also to the right hand side to oppose the change. And both of those, therefore, increase equilibrium yield, and that causes also the equilibrium yield to go up. So these are all powerful things that we can do to make more manufacturers use these techniques to make as much stuff as they possibly can. And that's where we'll stop. I hope that was somewhat useful.